I'm going to show you how I made the modular DMX lighting rig from my first video, and I'll give you some updates about a version 2 that's currently in development. I built a modular DMX lighting rig a few years ago, and after releasing a video about the system back in March, I've received a ton of questions about how to build it. So in this video, I will be going through the step-by-step process for building some of the parts in an attempt to answer as many questions as I can. And if you haven't seen the original video, I recommend checking that out first. I'll be breaking down exactly how I built the base and socket system, so hopefully you can easily build your own. I will also go into some more detail about the two separate distribution boxes that I showed in the previous video, as well as some of the more tedious steps in building both of the tube fixtures and the light bulbs. And throughout the video, I'll touch base on some of the updates and features I will likely be incorporating into the version 2 of this rig. So with that being said, let's start with the bases. The bases are the core feature of this rig, which allow you to hot swap between different fixtures using a proprietary 4-pin socket which I originally designed using PVC and ABS parts from Home Depot. I have had a ton of requests to design 3D print files for these parts, which I have since done, but for those of you that don't have a 3D printer, the non-3D printed version is still a very robust solution that I think actually has its benefits over the 3D printed version. I will go over the assembly of both the 3D printed and non-3D printed versions in this video. For each of the non-3D printed bases, you need a few components. Simply multiply the number of components by how many bases you need to make. Each base will require a 2-inch ABS cap, some 2-inch ABS pipe, which we will be cutting to 2-inch sections, a 1 1/4 inch gray electrical conduit coupling, a 1-inch gray electrical conduit coupling, a 3/4 inch white plumbing PVC coupling, some 1/2-inch by 1/2-inch C-channel aluminum trim cut to 3 8-inch lengths, 8 1/2-inch 832 machine screws, 8 832 nylon locking nuts, one 16mm 4-pin aviation socket, 4 tent pole springs, some smaller gauge wire. I recommend 22 gauge, but really any small gauge wire will work here, solder, electrical tape, and hot glue. Now, many of the pipe and coupling parts that you need from the store are actually not meant to work together, so don't be alarmed when you have to grab parts from multiple sections of the store. When I was originally figuring this out, I spent hours at my local Home Depot walking between aisles to find the pieces that fit together just right. For example, you might be wondering why I'm using a mix of the white plumbing PVC fittings and the gray electrical PVC fittings, and I did this because the gray couplings are much shorter than the white ones, which allowed me to make the sockets as low profile as possible. I also found that the white 3/4 inch coupling also fits a little more comfortably in the gray coupling, and the gray coupling has a more substantial ridge on the inside, which I think makes for a more usable and stable socket. You could theoretically use white PVC couplings where I used the gray, but I preferred switching to the gray for those reasons. And I know some folks have had trouble finding these exact parts, so to make it easier, I've grouped these parts based on the sections in the store that they can generally be found in, and listed them below in the description along with the Home Depot links for each part. For all the other parts that need to be ordered online, I will have the Amazon links there as well. Now on to the actual build. To start, you will want to build the base and legs, which the socket will be mounted inside. You will need to drill 4 holes on the bottom of the 2-inch ABS cap in this T-shaped pattern to attach the aluminum C-channel legs. I drilled the holes at 4mm, which is just big enough for the 832 screws to fit in snugly, but a 3/16 hole will be fine as well, just a bit looser. I marked a line down the center of the cap and placed the first hole at about 7/8 of an inch down the line from the edge of the cap. A tip for finding the center line of the cap is to use an engineer square and carpenter's square like this, which will give you the exact center line of the cap. I then marked the second hole on the line at about 3/4 of an inch from the first hole. I then drew a perpendicular line across the first hole and marked 2 more holes at about 7/8 of an inch from the first hole and drilled. Once you've drilled the first cap, you can easily transfer the hole measurements over to all the other caps. The cap also needs to house the 16mm aviation socket, so I sanded down the edge at the bottom of the T-bolt pattern flat to about 3/4 of an inch, and then drilled a 16mm hole with the center about 7/16 of an inch from the top of the cap to accept the aviation socket. I used a belt sander to sand the cap flat, but a file should do the trick as well. One thing to note about the aviation socket, I drilled the hole in the cap at this specific location because it allowed the nut for the socket to actually sit flat against the bottom of the cap, preventing it from spinning loose, meaning that the actual socket has to be rotated into the nut during installation. This means sometimes the socket might end up sitting lopsided or upside down once installed, but I preferred this over the potential of the nut ever coming loose. Once you've drilled the hole, hang off on installing the socket for now, as you will want to solder the wires on first. I then cut the aluminum C-channel to 3 8-inch lengths using my chop saw and drilled 4mm holes, about 3/8 of an inch from the end in all three. Since this C-channel is aluminum, you can cut it with a standard wood blade on your chop saw, but just be careful and go slow. If you don't have a chop saw or you don't feel comfortable using one on aluminum, a standard hacksaw will work here as well. For the middle leg, I lined the top hole up with the top hole in the base and marked where the second hole needs to go in the leg. Now the legs can be bolted onto the cap using 4 of the 832 bolts and locking nuts. At this point, you should have a base with 3 legs, 2 of which can swivel out into the tripod position. For the actual socket, I used the 1-inch electrical conduit coupler and marked 4 points equidistant from each other on the top. Now, all these couplers are actually tapered and one side is a bit wider than the other, so for the 1-inch coupler, you want to make sure that the wider side is the top to ensure the best fit between all the pieces. In my case, the couplers have some writing on one side, and this writing indicates the bottom or narrower side of the coupling, and I can't say for sure if yours will be the same, but you should be able to eyeball this at the least. Marking the 4 equidistant points can be done in many ways, and the way I did this originally was to take a set of calipers and measure the outside diameter of the coupler first, and then using that measurement, I used some basic trig to calculate what the distance from each point needed to be. There are probably a bunch of ways you can do this accurately, but let me know in the comments if you have a better way of doing this. Realistically, it doesn't need to be super accurate, but since you will be transferring these measurements onto all of the other sockets you make moving forward, it would be good to get this as close as possible. Once you have the points marked, take an engineer's square and mark a line down the coupler at each of the points. Next, I marked a couple lines around the coupler at 1/4 of an inch and 1 inch from the bottom. I then drilled 4 3/8-inch holes where the upper line intersects with the 4 vertical lines and 4 1/4-inch holes where the lower line intersects with the vertical lines. I also marked one spot between 2 of the vertical lines and 3/8 of an inch from the bottom of the coupler to drill a 1/2-inch hole to accommodate the wires coming off the aviation socket. Finally, I took an engineer's square and drew tangential lines from the edge of the 4 3/8-inch holes up to the top of the coupler and cut these lines with a hacksaw to make 4 slots. Next, I cut the 2-inch ABS pipe to a length of 2 inches using a chop saw and notched out a 3/4 inch by 1 inch square in the bottom using a hacksaw to allow the pipe to slide over the aviation plug. I also had to cut these smaller notches to accommodate the 2 bolts inside the cap. You can insert the pipe and mark where it lines up with these bolts to make it easy, and then you can use a file here to quickly make the small notches. This piece will be the main housing for the socket, but you will notice that the socket still needs to be held in place by something. That's where the 1 1/4 inch electrical conduit coupler comes in. You will want to cut this coupler in half, but you need to make sure that some of this little ledge inside the coupler remains, as this is the feature that holds the socket in place. Now, due to the slight taper on this coupler, you can't simply cut this on your chop saw in one go, as you will end up with a slanted cut, which could run the risk of eliminating the ledge feature that we need. So I opted to cut these with a hacksaw. I just use my calipers to check the depth of the ledge from either side of the coupler, which in my case was 31/32 of an inch, and transferred that measurement to the outside of the coupling and made sure to cut right between those two lines. Using a hacksaw has the added benefit of a much narrower blade, so if you are careful, you can probably get away with cutting the ledge perfectly in half, giving you two usable halves of the coupler. Now you should be able to do a test fit to see all these pieces come together. Since the coupling you cut in half is tapered, you will find that some fit looser inside the 2-inch ABS pipe than others. I just used some electrical tape around the piece to make the fit a bit more snug. Once you make sure it all fits together, carefully separate the ABS pipe along with the coupling from the base and apply hot glue on the other side to lock these pieces together. The next piece you will want to make is actually part of the light fixture and not the socket, but I think it's important to make this piece now to make sure you get the socket just right. Take the white 3/4 inch plumbing PVC coupling and find the side that fits into the socket best. You'll notice even this coupling has a slight taper to it, though it's much harder to tell just by looking at it. Just slide the piece into the socket and make note of the side that fits looser, which will be the bottom. In my case, the looser side is the one with less writing on it, but yours may differ. I then marked a line around the coupling at 3/8 of an inch from the bottom before reinserting the coupling into the socket. I then used the slots of the socket to mark 4 points along the line where you will drill 4mm holes to insert the remaining 4 832 screws and nylon nuts. These screws will be the electrical contacts that engage with the socket, which you will wire your LEDs to when you start building the fixtures. But for now, we will just use this piece to form your electrical contacts in the socket. At this point, you should have the main form factor of the base complete, so now we have to add the electrical contacts into the socket. I stumbled across these tent pole springs, which work perfectly as electrical spring contacts, and the ones I got originally were these 7mm wide by 40mm long double-sided springs with 5mm buttons on each end. These unfortunately are not always available on Amazon in my area, but this design only requires one of these little buttons, so these single button ones that I've linked down in the description should work just fine. To fit them into the socket in a way that will provide proper electrical contact with the fixture, simply insert your fixture plug into the socket and make note of where the screw heads land. The goal here is to bend the tent pole springs in a way that will kind of grab onto the screw heads to give you a nice electrical connection. In my case, I utilized the original bend in the spring to form this section, which meant I simply had to make one bend at around this point, which curves the contact into the socket. I then cut the spring here to make sure that the screw head doesn't get caught on it when inserting the fixture. Once I got the shape of the contact right, I started drilling little holes through each of the buttons, which will allow you to feed your wires through. Just make sure the hole you drill here is big enough to fit whichever wires you choose to use. Next, you'll want to get a soldering iron out and start soldering the small wires, which I cut to about 2 inches, to the aviation socket. The aviation sockets have little numbers for each pin, so you'll want to make note of which wire goes to what number and maintain this numbering throughout the rest of the rig. In my case, I'll wire red to 1, green to 2, blue to 3, and yellow, which will be the voltage line, to 4. I find having some little helping hands here can be super helpful, but it's definitely not necessary. Once you have the wires attached to the aviation socket, you can thread the socket into your base, holding the nut inside the cap. Now thread the wires through the large hole in your socket and pull each wire through the 4 smaller holes, making note of which color wire is going through which hole, as you must keep this uniform across all the bases you build. It would probably be smart to label the socket at this stage because the wires won't be visible from the outside after this point. Now we can thread the wires into the buttons of the contacts and solder them. The springs can be a bit finicky to get the solder to stick, but just apply lots of heat and be patient. Eventually you will see the solder bubble pool up inside the button, which is what you want. Finally, take some electrical tape and wrap the socket holding the contacts into place. The wires coming into the socket will get in the way a bit, but just do your best to work around this. Now you can put the cover on and the socket is complete. I promise once you do one, the rest will go far, far quicker. If when inserting the fixture into the socket for the first time you find it too tough to get in, or you notice that the housing actually lifts out of the cap a little bit, it's likely that your socket contacts are a bit too long and they are pushing up against the inside of the housing. Just give them a bit of a trim and adjust your bends accordingly. The 3D printed socket should have very similar assembly steps, but with a few less cutting and drilling operations. Notice there are some minor differences in the design, but these were all added in an effort to combat some of the weakness that comes with 3D printed parts. I will admit I have only printed this single unit, and I can't speak on the overall reliability of this method yet, but I have seen a handful of people make this already on the Discord channel, which is also where you can find all of the 3D print files for free. I've even included the Fusion 360 file in the Discord in case you want to make any modifications. I've had many people ask what the overall cost of this rig was for me, and I've struggled to answer this as there are so many parts involved, each with differing cost considerations and whatnot, but I'll do my best to get a solid number together by the end of this video, starting with the bases. Keep in mind, I'll be using Canadian dollars, and I will give a per unit cost, assuming you are building a rig with 8 bases and 8 fixtures. After calculating all the parts used for the original bases, you'd be looking at approximately $200 for 8 bases or $25 per base. This will obviously vary for the 3D printed version depending on the amount of filament and what infill you decide to use, but I think it should be comparable. I made 2 different fixtures for this rig so far, the tubes and the bulbs. Both of these fixtures connect to the socket using the Schedule 40 3/4 inch PVC coupling. In both cases, I used these spade connectors which get tightened to the screws inside the coupling. In the case of the bulbs, I used a 3/4 inch PVC pipe inserted into the coupling where I could feed the long wires that connect to the bulbs at the end. For the tubes, however, I found these same 1-inch electrical conduit couplings which we used in the socket build fit perfectly inside these T12 fluorescent tube protectors, which is great because the other side of the 3/4 inch couplings already fit tightly inside these couplings as well. To mount the LEDs inside the tube, I attached them to this flat aluminum trim piece which I pre-drilled and installed these little chamfered machine screws to fit underneath the LEDs. I used clear packing tape around the LEDs and the trim to ensure they never fall off. Once I connected the LEDs to the screw contacts inside the coupling, I slipped the whole bar inside the tube and marked where the screws ended up, and I used a soldering iron to melt holes for the screws. I screwed the nuts onto the screws, but I left them completely loose for now, which is crucial for the next step, inserting the parchment paper. In my original video, I mentioned that after trying a bunch of different options, I found plain parchment paper offered the best diffusion by far, which is great due to the cost and availability, but getting the paper to sit inside the tube is arguably the most difficult part of the entire rig build. I did, however, come up with a method that works pretty well. First, I cut the parchment paper to just under the circumference of the tube, just small enough so that there's a tiny gap along the back to let the paper slide past the screws holding the LEDs in place. I then took the end of the paper that I will be inserting into the tube and folded the corners over so that they don't get caught on the screws as you slide it in. Then gently roll the paper up and slide it into the tube, trying not to introduce any crinkles in the paper. You might find the paper wants to twist a bit, but you can actually steer the paper by pushing on either side as you insert it. Once you get past the second screw though, you should be golden. Now that the paper is fully inserted, tighten the nuts holding the LEDs, and this should hold the paper firmly in place as well. For these cost calculations, I will just estimate the cost of an 8-foot tube, as these will be the priciest due to the sheer number of LEDs. When I built these originally, I couldn't find an online source for quality LEDs, so I went to a local LED shop that had some premium quality LEDs that I could guarantee would have amazing color accuracy and durability. But with the selection I'm seeing on Amazon these days, I wouldn't really recommend going this route now. I believe I spent over $100 per 16-foot roll for these premium LEDs, which are still working great, but on Amazon, there are countless options in the $20 to $40 range that have excellent reviews and are probably going to work just as well for this application. In this build, I used 12-volt 50/50 SMD RGB LEDs with an LED density of 60 LEDs per meter or 300 LEDs for the entire 16-foot roll. You don't have to use these specific LEDs, but I found the density was crucial for getting that seamless light inside the tube. If you go any less dense than these, you'll likely see hot spots where each LED sits. I should also mention that a ton of the LEDs I found on Amazon lately are RGBW, meaning they have an extra channel that controls just a white LED alongside the red, green, and blue ones. And this is nice to have, however, these would require an additional electrical connection within the base, cable, and DMX decoder, so if you want this feature, you'll have to accommodate for this extra channel. I found with good quality LEDs, maxing out the red, green, and blue channels will give you a very workable white color, so I was happy to just stick with these. I have linked an option that looks great in the description below, though I haven't ordered these exact ones myself yet, so I can't exactly speak on their quality, but anything with these same specs will work for you. So considering these better LED prices, which are still conservatively high, you should be looking at approximately $55 per 8-foot tube fixture, and considering these specific fixtures are the most expensive ones I made, you could drastically reduce this cost by going with shorter tubes or trying the bulbs or even designing a fixture of your own. I've had a few questions about the cables as well, and while they are pretty straightforward, there are a couple little quirks I wanted to touch base on. So the cables I went with on my build were heavy-duty 16-gauge 4-conductor cables, and the reason I went with such thick gauge is because of a thing called voltage drop. When I started building this rig, I didn't know what that was, and partway through the build, when I was looking for the right cables, I started learning about this and realized that I needed to take this into consideration when selecting the right cables. At this point, I had already purchased the LEDs, which were 12 volts, and I knew I wanted these cables that run from the distribution box to the bases to be 20 feet long. I also knew that the largest fixtures I'd be using were the 8-foot tubes, which I calculated use about 36 watts each, and at 12 volts equals a maximum of 3 amps of current draw at full brightness. So with all this information, I actually had everything I needed to determine the appropriate cable gauge for my system using this voltage drop calculator on the internet. So in my case, with 12-volt LEDs running up to 3 amps at a 20-foot distance, if I went with the standard 22-gauge cables that tend to come with these LEDs, I'd be looking at a voltage drop of around 16%, which equates to about 2 volts of loss by the end of the cable. This would mean that my LEDs would only be getting 10 volts, which would mean dimmer lights overall, and those extra 2 volts would be converted to heat along the cable, which obviously is not good. After some research, I decided I wanted to keep my voltage drop to under 5%, so I went back to the calculator and started changing the cable gauge until I achieved this, which is how I landed at 16 gauge. Now, had I known this prior to purchasing my LEDs, I would have probably opted for 24-volt LEDs instead of 12. They are slightly more expensive, but I would have been able to use 22-gauge cable because not only would I be doubling the voltage, which lowers the voltage drop of a system, but I'd also be cutting the current in half to only 1.5 amps, since the 24-volt and 12-volt LEDs would be running on the same overall wattage. Now, I would suggest you consider building a 24-volt system as opposed to a 12-volt system, as having thinner cables would reduce the overall weight and cost of the entire system, but, and this is a big but, as I've been looking at version 2 of this rig, I am seeing the limitations of the variety and availability of certain LEDs in the 24-volt range, specifically when you start looking at addressable LEDs. They do exist, but if I were to commit to a 24-volt system now and went with the thinner cables, I wouldn't be able to switch back to 12-volt LEDs unless I changed all of the cabling too. However, if I started with a 12-volt system and wanted to switch to a 24-volt system later, I could use the same cables as they'd be more than heavy-duty enough already. Now, the last thing I wanted to touch base on regarding the cable was the actual size of the cable in comparison to the aviation plugs. I didn't realize the 16-gauge cables I purchased wouldn't actually fit inside the housing of the aviation plugs, and I tried to modify them, which kind of worked, but at the end of the day, it was just way too much of a hassle, and I ended up just stripping the casing back and wrapping them in electrical tape. Some heat shrink here would have been a bit more elegant, but still not a perfect solution. And I haven't really figured out a better solution for this yet. Maybe I need to find larger plugs than the 16mm aviation plugs, or I need to find 16-gauge cable with a thinner casing, but I'm still working on this, so if anyone has any ideas, let me know in the comments below. So these are just some of the things to keep in mind regarding the cables when you build your own system. I think a 24-volt system could be really cool, but it could limit your LED options, so I just wanted to lay out all of the considerations I have been making with the development of version 2. When I bought my cables initially, I could only find them at a commercial cable company that was in my area, and they had a minimum purchase of $500, so I bit the bullet and had to buy way more cable than I needed. However, like the LEDs, I am seeing way more options online for 16 gauge cables, so just using this Amazon listing, for example, for 100 feet of cable at $88.88 Canadian, if you needed 8 20-foot cables, you'd probably want to order 200 feet just to be safe, and adding in the aviation plugs on each end, where a pack of 20 costs $27.40 on Amazon, you'd be looking at just over $200, minus the cost of solder and tape for all the cables, with enough to make an extra cable or two, or about $25 per cable. The original distribution box I made for the system was honestly pretty ridiculous. Having the built-in reels did make deployment nice and quick, and teardown was pretty smooth as well, but it added a ton of bulk to the system, which didn't make flying with them very practical. If you did want to make a similar reel system for your build, there are some things I'd consider. My budget was minimal when I built this, so the materials I used were the cheapest I could find. The reels were made from styrofoam sandwiched between two hardboard discs, and the reels just sat on some metal electrical conduit. Upon my initial testing of the system, I found that the reels would not unwind properly and it would just get super tangled really easily, so I had to add this apron sort of thing to prevent the cables from doing whatever they wanted. I also had to settle for the fact that I was still going to have to plug the lights in every time, as the reels couldn't rotate unless the wires were unplugged at this end. I mentioned this in the first video, but if I were to build this again, I could use some slip rings so that I could keep the electrical connection while being able to rotate the reels freely. But ultimately, I think the most elegant solution to this problem is to create bases with built-in spools so that the spools themselves can be pulled out of the case and placed on stage without ever having to unplug them. This is ultimately the solution that will be utilized in version 2. Now, the second distribution box I mentioned in the video is very simple. I just grabbed this electronics enclosure from my local electronics shop, and I actually had to take the casing off my DMX decoder to fit it inside because it was just slightly too big. The main thing to note about this distro is that I couldn't fit a power supply inside and had to use an external power supply for this version. Essentially, this enclosure is just a slightly more robust version of the case that is already on the DMX decoder that incorporates the aviation plugs I used for the rest of the build, but you could easily just use the DMX decoder by itself in this case. I was able to get away with the smaller power supply because the fixtures I was using at the time were very small, so I only needed a low amp power supply, but if you were planning on using large fixtures like the 8-foot tubes, I would consider using something more like this. This is a simple enclosure I designed that allows you to place a large 30 amp DC power supply inside along with the DMX decoder. I admit I haven't actually printed this out yet, but there are some people in the Discord that will be trying this design out, and as soon as we confirm it works, I'll make the file available for everyone. Now, I've also seen a few folks just using larger ready-made enclosures, which seem to work well, so the options here are endless. As for the costs here, I will calculate the main components inside the box, but I won't include the cost of the actual box itself, since I think this will vary drastically depending on what your goal is. Keep in mind, there are a few other options out there for DMX decoders and power supplies, but assuming you want to make the 8-fixture rig, you will need at least a 24-channel DMX decoder like the one that I used. And just to make sure you have more power than needed, I'd suggest a 12-volt power supply like this, which at 360 watts or 30 amps at 12 volts will have enough juice to continuously power 8-foot tubes at full brightness. If you don't need such a beefy power supply, you could grab a 12-volt laptop power supply, but the cost isn't that big of a difference. The only real benefit to using a smaller power supply like this is that you can get ones that don't have any exposed high voltage contacts and won't require any sort of additional enclosure, which might be a major benefit in your case. Also, I'm not including the 8 aviator jacks in this breakdown because I included them in the cable cost calculations already. So when factoring in the DMX decoder, the power supply, the XLR panel mount jacks for the DMX connections, and the power cable and jack along with a $20 buffer for a case or extra things I might be forgetting, you'd be looking at just around $200 for the distribution system for the entire rig. So after adding up each section of the rig, you'd be looking at just around $1,000 Canadian if you did it pretty close to how I did mine originally. Of course, there are so many factors to consider, so your experience may vary drastically in cost in the positive or negative direction, but I hope this gives you some idea of what you're getting into. And keep in mind, this is an 8-fixture rig with 8-foot tubes, and once you build this and you want to buy a new set of completely different fixtures, you won't need to buy the bases, cables, or distribution system again. As an example, when I was asked to build the bulbs, I probably only spent around $100 or so for effectively a whole new set of lights. So this video is already a bit on the long side, but there are a few other questions I wanted to just answer quickly. I have had a few folks reach out looking to have me build this rig to sell, and while I'm thrilled that this rig has gained so much interest, I never felt this version of the rig was refined enough to sell as a product. Which is why I've teamed up with a couple super smart guys down in Texas to help me make a version 2 of this rig that we will hopefully be able to sell as a kit. Without getting into too much of the details right now, our goal here is to develop a completely open source product and ecosystem that will allow anyone to get started building a highly cost-effective and powerful modular light rig that will be able to grow with your needs. Now, for those of you that are eager to get a light rig going now, but aren't sure if you should wait for V2 to come out, I will be making sure that as many of the parts and fixtures of V1 will be compatible with V2, so if you decide to upgrade later, you should be able to do so without too much fuss. I don't want to commit to a release timeline for V2 in this video, but if you join the Discord channel linked in the description, I will be keeping everyone in the loop as best as I can there. Probably the most asked question I've gotten so far is, can the rig be built using addressable LEDs? The short answer is yes, kind of. Since most addressable LEDs only require 3 to 4 electrical connections, the cables and bases and power supply will totally work for addressable LEDs. But you would need to swap the DMX decoder out for a pixel control module, which I am currently looking into right now, so I don't have a perfect solution to suggest for this yet. So it's totally possible, with some alternative parts, to make the system work with addressable LEDs. In fact, some people on the Discord have already started doing this, and this will be a major new feature in version 2. Now, controlling addressable LEDs is a whole different issue, which we're hoping to solve with the version 2 rig. In fact, controlling the light rig in general got a lot more difficult since I recently found out the DMX box I was using in my original video to program my lights is discontinued. If you already have a DMX box, they do seem to still work great, though they wouldn't work for addressable LEDs at all. Now, if you need something new, there are a few options out there, including the EMU system by Entech, which I've heard lots of great things about, despite the fact that it is subscription-based. I think this EMU system is worth checking out until we come out with our solution in version 2. So that's it for now. I hope this video answered any questions you might have had after watching the original video. As always, please leave any comments down below and I'll do my best to answer any questions there, but also feel free to join the Discord channel linked in the description for some more in-depth information. I'm so excited to share the version 2 rig with you guys, and we are working hard to get this out as soon as possible. In the meantime, please drop a like and hit the subscribe button if you find value in this type of content. Now, I never intended for this channel to become a lighting focused or tutorial channel, and in general, I'm just hoping to share my design and building process on a wide range of different projects, but all your feedback has been so exciting, and I wanted to make this video to help you get started building this rig. With that being said, some of the videos I plan on releasing in the future are not lighting related at all, and if you are just here for the lighting stuff, that's cool, and I will continue to dive deeper into developing cool lighting projects for sure. But if you enjoy seeing me design and build new ideas, some practical and some not so much, I hope my non-lighting related videos will have some value to offer as well. Thank you for all your support, and I'll see you in the next video.